Okay, so I've got a hard act to follow. That talk on genomics was actually very interesting. Mine is a demo, so it's demo time. Most of the time we're going to be spending during this talk is actually launching a cluster. So imagine you're a researcher. You want to run a larger job, but you don't have the resources, or maybe the queues in your university or lab's cluster is days or weeks and for your job. So what we're going to do today is see what it will take to launch a roughly 1,000 node cluster, or 1,000 core, sorry, 1,000 core cluster on AWS. It's actually a fairly easy process. There are many ways to do this. We have a lot of partners who have their own methods. What I'm going to show is something called AWS Parallel Cluster, which is a new service that we launched a little less than a year ago that makes launching a cluster actually fairly easy. It involves a configuration script, which I'm going to show you. It involves a simple command line launch, which I'll show you. And then we're going to launch a cluster. What I'm going to do is launch the cluster in a way where we get the head node, which is the primary way we access the cluster, with no compute nodes, because we don't want to pay for compute nodes until we need them. Then I'm going to launch a job, a very simple job, that's going to launch my compute nodes as I need them, and then when it terminates, they will disappear. With AWS, of course, you only pay for what you use, and therefore it's nice to have your compute nodes launch and then disappear and only appear when you need them. So with that, let me go to my demo. Okay, so I've got a PC. For those of you that use Macs, this is a little bit easier because you've got native Linux in the background. For me, it's a little more complicated because I'm on a PC running Windows, so I have to have some sort of emulator. You can use PowerShell if you're brave enough, or you can use some sort of Linux interpreter. I'm using Git Bash. You can use just about anything. I've created a script, so I'm just going to go quickly start that script. This is about 30 lines of code. It's not very complicated. We're going to go through this after I start launching the cluster, because it'll take about 5-6 minutes for the cluster to launch. And we'll go through this and talk about what's in there. And it's actually not that difficult. Of course, for those who've never seen a script before, maybe it's a little challenging, but it's fairly straightforward. Let me go to the window where we're going to launch our cluster. So I'm going to do pcluster, oops, and I've got to call it, or I'm going to do create. That's my first thing. I'm going to call it a name. Let's call it Canberra. And I've got a config file, which, oops, now you can see how great a typist I am. That's probably our number one thing that gets in the way of our progress. And then I called my config file Canberra. How original. Okay. So this is going to now start creating my cluster. Will take a little while, probably about 6 minutes. Basically, we've got little elves that go and get all our parts for us and put them together and create a computer. Basically what's happening is we're launching our system, we're creating our file system, we're doing all this, and it takes a little while, just like it takes a little while to boot your laptop. So let me just go over to my config file, and let's go through this in the next 5 minutes and just talk about what some of these things are. Okay, the first 4 lines, pretty easy. It's just some global stuff. It says, let's check and make sure we have the current version of Parallel Cluster. It's pretty simple. Sanity, it actually goes through the file and says, do you have any typos? That's kind of nice, because if you just saw how many typos I had in that one line, that's a very useful thing. And then for my cluster template, this is based on something called CloudFormation. We have a template. So in back of this is about 4,000 lines of JSON code, which you don't have to deal with, fortunately. But I'm just going to use the default. There's no reason. I don't have any special circumstances here. In the region, I'm doing this in Sydney. I did this for the first time last night in my hotel room because I'm based in London, so I usually use one of the European sites. So I thought, I better make sure this actually works in Sydney. It does. So I'm using a region of the Sydney region. Now I get to the basic design of my cluster. Okay, so we're launching a real compute cluster, which is going to give us about 1,000 cores of Skylake, Intel Skylake processors. The first thing I need is I need to give it an SSH key. This is my name of my key pair. Any system you have will, if you have SSH, will need a key pair. How many of you use Slurm? How many of you know what Slurm is? Okay, a fair number of you. It's a scheduler. It's a job scheduler. You might think, why do I need a scheduler if I have my own cluster? I don't need to schedule anything. Well, actually, the scheduler does some things that are nice for us, like it manages all the different nodes. And so we still use a scheduler even though we're not really we don't really have a queue per se. We're not submitting jobs to a queue. The scheduler really is just helping us manage the multiple nodes. We can do that ourselves, but that's just too hard. So I'm just going to use Slurm, which is very popular in the research community. So Slurm is a scheduler. I have a post-install script. The post-install script is a bash file that does the final setup of my cluster. And it can be pretty complicated. It can install software. It can do all sorts of things. In my case, all it's doing is copying over 2 files, which we'll see when the cluster is complete. I have some settings that I'll go down. This is just pointers. I'll go down and show what those are in a minute. Compute instance type. For those of you in in the research field, you probably are familiar with a node. We use the term instance. An instance is essentially a type of compute node. In this case, I'm using a C518 extra large. That means that it's a node that has 36 Skylake cores, and I can't remember exactly how much RAM it has, but it's basically our C series of instance types have about 4 gig per core. The neat thing here is just by changing this one line of our compute instance type, we can change the essence of our core. We can actually have high memory nodes that have up to 16 gigabytes per core. We can change from, we can use our super fast clock speed, or Z1D. We can have local disks. We can do all sorts of things just by changing that one line of code. Our master instance type, this can be different. It doesn't have to be the same. In this case, I've got a Broadwell machine with 8 cores. This is a little bit smaller. I don't need anything. I want something to compile fast, but it doesn't have to run as fast, or it doesn't have to execute as fast. Next line, cluster type. I can do on demand, which means I'm going to get it right now. Costs more. I could do spot, which means that I get lower pricing, up to 70% savings, or as much as 70% to 90% actually for some instance type savings on the cost by using spot. The problem with spot is our excess capacity. If there isn't excess capacity, you might not get that availability right now. When you do an HPC job, many of the tightly coupled schemes, like in computational fluid dynamics, require that there's a low latency between nodes. So you don't want one node to be across the data center. You want them all in a certain group. So we choose to have something called a placement group. Dynamic means that as I add compute nodes, it's going to dynamically allocate them in proximity to each other. Okay? I can specify the size of essentially the disks that reside on each node. So this is going to include things like the local operating system. If you want to put data on each node, you can do that. I'm just going to have the operating system, so I just have 20 gigabytes. The master root volume size, 256 gigabytes. So that's like my hard disk on my laptop kind of thing. The initial queue size, that's how many compute cores I want to start with. 0. I don't really want any right now because I'm going to talk a little bit, and we're going to watch them launch. I'm going to put the maximum queue size at 28. I did that just because I didn't want to have too many for this demo. 28 will give me 1,008 cores, and we're going to use them all. I don't want to maintain the initial size. I could make this a cluster with a certain set of nodes that stays that size forever, or as long as I have that cluster up. But I'm going to let this be dynamic. We have something called auto-scaling. It will auto-scale. So supposing I'm a researcher and tomorrow I want 1,000 cores, but Friday or Thursday I only want 500 cores. I don't want to have 500 cores sitting idle, so this will expand and contract as needed. But it will always go down to 0 when I'm not using it. So when I go home at night and I'm not running anything, it goes down to 0, so I'm not paying for any compute nodes. When we do this last line here, extra JSON, is a little cryptic, but many times when we do tightly coupled codes, we want to turn off something called hyperthreading. Intel has so much parallelism in their CPUs that they actually they actually send 2 threads of work through a single CPU. But because we're normally doing computation in HPC, where we're using the same parts of that CPU, the 2 actually conflict with each other, so we turn off hyperthreading and only have one job per, or 1 thread per CPU. I mentioned the pointers. These pointers basically tell me where I'm going to put this, where in my virtual world I'm going to set this in terms of a VPC, a virtual personal cloud. That's the idea that says this is mine, this is my space. And then a subnet within that, which tells me what availability zone. And tomorrow when I talk, I'll talk a little about availability zones. You might hear that elsewhere. I don't want to go into that detail today. Finally, how big a disk do I want? What type of disk do I want, or storage system? In this case, I'm going to use an EBS, or a block file system. I'm going to give it a name, code. It's going to have 128 gigabytes. This is just a demo. I didn't really need that much. I could make this up to 12 terabytes if I wanted. In this particular case, it's also going to be SSD, an SSD disk. I could make a shared file system. We have FSX for Lustre. So that's a shared file system where all the compute nodes will share. In this particular case, this is just served off the head node. This is the kind of thing I can change very easily with just a couple lines of script. So if I wanted to do FSX, I would just launch that, and instead of having EBS volume, I would do an FSX volume. Very simple. Okay, that's the script. And that's the most complicated part of this. And if you're like me and a scrappy scientist, you just borrow someone else's and you make a few changes and you go. And that's basically all you need to do. So let's see where my cluster is. Okay, it's completed. Our cluster is launched. I have a master public IP address, which is right here. I have a private IP address. I'm going to go quickly to the console. And we're going to look at EC2. We're going to see this because I want to show you what I have right now running in Sydney. So this is our console. It tells me I have an R 4.4 extra large. R is one of our larger memory per core instances. It's based on the Broadwell technology. It's run through its checks. What I want here is the IP address. The IP address, of course, was here also, the public IP address. Now I'm going to go and I'm going to log in. I'm going to SSH into this. Oops, don't need that. If you're on a Linux box or a Mac, this is easy. I just type SSH in a command line. I'm using MobiXterm because I'm on a PC. Means a little bit extra step. So I'm going to copy in my, my remote host. I'm an EC2 user. So that's my username here. And now I have to give it my key pair. Remember, it was Canberra, it's sitting here. And I'm logged onto the head node. Okay. I can do some updates. It's telling me that there's some security patches I might want. Normally, AWS is continually updating our background operating system, but we can't keep up with everything, so you can do it yourself. I'm not going to bother because I'm just going to have this running slowly. Okay, the two files I uploaded hello world.c, a C file, and then run.sh. Run is just a script that's going to run that. So the first thing I want to do is I'm going to compile this. So I'm on the head node, so I'm going to compile my hello world file. Oops, oh, darn it. Ah. Oops. MPICC. What am I doing wrong here? -O, yes. That should be okay. There's always going to be something that's going to be hello world MPI. Okay, it's there, MPICC. I'm going to just type it in case I blew it. Oops, I need -O. -O. No such file or directory. Oh, did I just delete that? How did I delete it? What did I do? Jeez. Okay, well. You know, when something can go wrong, you know, it's like, it's amazing what you can do here. Okay, so I'm going to copy that. Fortunately, I have my scripts there ready for me. And at some point, I'll figure out, how did I delete that? Okay. That took a little while because that's files based over in London. Okay. Well, that little glitch, apologies. I don't know how I deleted that. Okay, so now I have my little compiled code. I am going to run, so I'm going to, let's look at sinfo. Okay, sinfo tells me I have no compute nodes. So running this file right now means that it's going to have to go find those compute nodes. So I'm going to run, I'm going to sbatch-n 1008. So I'm going to do this on 1008 cores. That's a maximum that I've told my cluster I could launch. And then run.sh. Okay, so it submitted that. I'm going to go back to the console really quickly, and we're going to look at what happens here. Now, I see that my master node is still running, but I have nothing else. I'm going to refresh, and I hope this doesn't take too long. I timed it last night. There we go. And you'll notice that I've just added 10 more compute nodes. They're pending. They're starting to launch because it says, oh, I need 1008 cores. I only have none right now. And so it's starting to launch them. And as I refresh, it will, we throttle a little bit because we don't want someone going and asking for 1 million cores all at once. By the way, I have had a colleague launch 1.3 million cores in our spare capacity in London. So the amount you can get is sort of astronomical. This is actually small, this 1,000 cores. Okay, it's launched another 10. So this throttling prevents someone from just going and hosing the system. So we do 10 at a time. I've just launched 10 more. When I get to 29, since I've launched 28, I'll be done. That'll take a little while. You'll notice that these are all initializing. They're running, but they're initializing. Okay, so it's just kind of like booting, basically. Okay, and now it's grabbed the last few. Okay, so we have to wait a little while. Imagine each one of these little compute nodes is booting up, just like you turn on your laptop. So it'll take a couple of minutes. They all have to go through their boot sequence and load up what they need. Load up MPI. So what this little example that I'm doing is pretty simple. All it's going to do is submit a job that's going to go to each core and say, hello world. Okay, so we're going to see hello world 1,008 times. Very exciting. But I still have not found the right simulation that I can do in a half an hour demo that would actually solve the world's problems or solve the weather patterns over Australia. You know, we run weather codes like WRF and Cosmo. We run CFD codes like OpenFOAM, Fluent, and many others. Unfortunately, those demos take a little bit longer to run. So I just do hello world so you can kind of so you can see what's going on. Okay, so they're still initializing. Many of them are still initializing. Let's see if any are up, finished yet. No, not quite. If I go back to this, I can do sinfo, and it still says 0 nodes because the nodes have not come online. But in a couple of minutes or so, we'll start seeing that nodes will start coming online. This is taking a lot longer than it did last night in my hotel room. Oops, okay, okay, so they've booted. Now Slurm is going to, it regularly checks. This is actually something that's different than an on-prem facility because nodes come and go. Slurm has to continually check and see who's around. But let's see what it's finding. Okay, so now it's found 11 of the nodes. Of course, as soon as it gets 28 of the nodes, it's done. It will run the job. The job's going to be very fast because all it's going to do is say, hello world, and it's done. Okay. Again, because some of them came up a little bit later, they'll take a little bit longer, but we can go back and look and see. More and more are coming up. Slurm's going to slowly find them. 25, okay? Just need the last 4 nodes and my code will run. Obviously, this isn't terribly efficient if all you want to do is run a script that runs 1,008 hello worlds. But if you're running a long, 3-hour job, this is not a bad way to go. 28, okay. So now it's probably run. I can look at my output file. I've got a slurm.out, so let's just look at that, see what it says. And it's very exciting. Oh, it's told me that all these different nodes have checked in. Actually, this is unusual. It's unusual because they're in numerical order. Usually they're kind of randomized. I mean, they do, oh, here, you've got 1 and 0 and 1 down here. But, basically the nodes come up and each core sends its signal, hello world. It's done. It now has completed the job, and that core then is available for something else. Okay? But, take my word for it that there's 1,008 hello worlds here. Very exciting. Okay. So now what's going to happen is those compute nodes are going to stay up for a certain amount of time that I've specified. The default is 10 minutes, and I didn't change that. So we're not going to wait around and watch them disappear. It takes, we're not going to wait 10 minutes. But if I'd set it to a lower time, 1 minute, for example, then in a minute from now, we would start seeing all those cores start, or all those nodes start turning off, shutting off. So we've only paid for what we've used. Many researchers are starting to use this, and it actually is what really is the #1 reason people save money, is because you don't have to figure out how you're going to provision your cluster ahead of time. In this half hour, we have launched a cluster from scratch and gone up to 1,008 cores. As I said, my colleague in London has launched 1.3 million cores. They're not all the same type as they are here, where they're Skylake processors, but the amount you can get is flexible. If tomorrow you only want to launch 10 cores, that's easy. Just launch 10 cores. And since you're only paying for what you use, you're saving money. You don't have to go buy a massive cluster to support your research when you don't know how many cores you're going to need. You don't know how to provision ahead of time and how many people are going to use it. The neat thing about this is I've got this script, and if I want to run 2 jobs and they take, let's say, a day, I don't have to wait and submit the next one tomorrow. I can actually launch 2 clusters. I can launch 2,000 core clusters side by side and run them both simultaneously. And instead of waiting 2 days for my results, I get them both in 1 day. So we've got a customer, TLG Aerospace, who does CFD calculations. They used to have to schedule on their on-prem cluster their workload so that it took about a week, and then the second week they would do the analysis. Now they launch it overnight, do all of the runs simultaneously, launching multiple clusters, get the results, and by Tuesday morning, if they launch Monday, by Tuesday morning they've got the results and they have the rest of the week to analyze. It's sped up their workload. Because you only pay for what you use, it doesn't matter if you do them all at once or you do them serially. So you might as well do them all at once and get them completed. Okay, so I just have a few minutes left. What I need to do now is shut down my cluster because I don't want to pay for it. I'm not paying for it. Jeff's paying for it. Okay, so I'm going to pcluster, delete. Oops. Canberra. And it will start deleting cluster. And I can go and very quickly I can start looking at my, my compute nodes will start shutting down and I'll see them disappearing. I hope no one wanted me to run some other simulation because it's too late now. Not that I had anything prepared. Okay, so while this is shutting down, just a curious, we have about 3 minutes for Q&A, I think. So does anyone have any questions? Yep. Yes. So if you were to say, I want my initial number of compute nodes to be 10. So it launches and it launches 10. And that's a normal thing to do, actually, if you don't want to wait and have them come up later. They can, initially, you can have 10 nodes. If you don't use them, then they start disappearing. I do a lot, that happened a lot to me with customers, because I'd sit there with a customer and you'd launch 10 and you'd say, show them the 10 nodes are there and, oh great, you know, now let's use them. And then you sit and chat for a little while and all of a sudden 10 minutes later it's like, oh my God, they're disappearing. I tend to just start with 0. You can start with whatever you want, but they will disappear. And that is, okay, now we can see them shutting down. That is a parameter you can set. You can say how long do you want it to last. If you have a bunch of jobs and you know that they're going to come serially and maybe a half an hour apart, you could set that to 30 minutes and they'll stay up for 30 minutes. Sometimes you want to look at a result and say, you know, kind of decide if what you want to do next, change your input parameters and submit another job. Sometimes that takes a little longer, so you can set that for that time for whatever you want. Yeah. What is the interconnect? So that's a good question, because we've done a lot of work with our interconnect. Most researchers believe that you have to have InfiniBand. If you don't have InfiniBand, you don't have a good cluster. Most workloads are actually, the latency is memory bound. So about 80%, 80 to 90% are memory bound. For those workloads, we do really well, even without our high performance network. We have a choice. I don't have it, I didn't set it up here, but we have something called EFA, Elastic Fabric Adapter, which halves our latency. And we have found that with many workloads, computational fluid dynamics in particular, we actually compete very favorably with on-prem craze and so forth. I just did a benchmark with Cosmo where we compete quite well with a supercomputer, quite favorably. And by favorably, I mean there's one, I can't talk about who the customer is right now, but we did some work with a customer and compared to Archer, which is the UK supercomputer system. It's a Cray, and it's a little bit older, admittedly, but we were half the speed. In other words, we were twice the performance. And even scaling out to 2,000 cores, we were still over 30% faster than the Cray. And that's with our faster, actually that was without our faster internet. We haven't even tested our fast interconnect yet on that. But we like to think about what does the workload do as opposed to what's the network speed, because the network speed is only one indicator of how things are going to run, and we really like to look at the workload. Admittedly, there are workloads that aren't as good on AWS, quantum mechanics type workloads that need to have a lot of data dependency across all nodes, don't scale out to 2,000 cores, for example, as well on AWS as they might on a machine with InfiniBand. Yeah, okay, so our highest bandwidth network is 100 gigabit per second, okay? And you get that with our C5N, an M5N, a P3N right now, just those two, but we're going to extend it to other families, so that's 100 gigabit per second. Yep. Each type of node will have a different maximum. So, for example, I think our M5s now are 25 gigabit per second. But, one thing I always say is AWS is not standing still. Our networks are getting faster and faster. It's also, I should also add that our network is different than than what people have experienced before when they've run clusters, in that it's a point-to-point network as opposed to a backbone type network. And that actually speeds up communication because nodes can talk to each other as opposed to going across a backbone where you're your own noisy neighbor. Any other questions? Okay, well, I'm 2 minutes over, so I think that's probably good timing.